Hello everyone, welcome back to my channel. In this video, we are going to perform the complete load setup and analysis configuration for our ETABS building model. This includes defining and assigning all gravity loads, seismic loads as per IS 1893:2016, wind loads as per IS 875. Part 3. Verification of diaphragm assignment and application of cracked section property modifiers as per IS code-based design practice. This is one of the most critical stages of modeling, because incorrect load definition or incorrect stiffness modifiers will directly lead to unsafe or unrealistic structural behavior. So I strongly recommend watching this video carefully and following each step properly. First, open ETABS and load the same project file that we have been using in all previous videos. This model already contains grids, story data, beams, columns and slabs, material and section properties, supports and basic geometry. Now we will convert this basic geometric model into a fully functional structural analysis model. Step 1. Initial analysis and model health check. After opening the model, the first thing we always do is run a trial analysis. Go to Analyze Right Pointing Arrow Run Analysis. This helps us verify connectivity of elements, support conditions, stability of the structure, and any modeling mistakes. Carefully review any errors or warnings. We will also visually check joint displacements and make sure there are no unrealistic movements, such as excessive drift or instability. Only after confirming that the basic model is stable, we proceed to load definition. Step 2. Review existing load patterns. Now go to Define Right Pointing Arrow Load Patterns. You will see that dead load is already defined with self-weight multiplier equal to 1. Live load is defined with self-weight multiplier equal to 0. This is correct modeling practice. Dead load automatically includes self-weight of structural elements, while live load does not. Step 3. Define seismic load patterns as per IS 1893:2016. Now we will define the earthquake load patterns. Go to Define Right Pointing Arrow Load Patterns and click on Add New Load. Create a new load pattern named EQX. Set load type as seismic. Set self-weight multiplier as 0. Select Auto Lateral Load as IS 1893:2016. Click Add New Load. Similarly, create another load pattern named EQY for the Y direction. This separates earthquake effects in both principal horizontal directions. Step 4. Define seismic parameters. Now go to the seismic parameters window associated with IS 1893:2016. Here, carefully define seismic zone factor as per project location, importance factor based on occupancy category, response reduction factor based on structural system, soil type based on geotechnical data, and damping ratio as per code. For time period, we will select program calculated, or alternatively we can use the IS code empirical formula if required. These parameters control the magnitude of seismic forces and must be entered correctly. After entering all values, click OK to save the parameters. Step 5. Directional control and load case setup. Now verify that earthquake loads are applied in the correct directions. Ensure that EQX acts in global X direction, EQY acts in global Y direction. Check sign conventions and directional assignments carefully. This ensures correct lateral force application. Step 6. Verify and assign diaphragm. Now we will verify the diaphragm assignment. Select slab elements and check if a diaphragm, for example D1, is already assigned. If diaphragm is not assigned, go to Define Right Pointing Arrow Diaphragms, define a rigid diaphragm, then assign it to all slab elements. The diaphragm ensures that flow slabs act as horizontal load distributing elements during seismic and wind analysis. Without diaphragm, lateral load transfer will be incorrect. Step 7. Apply cracked section property modifiers engineering reality. Now we will apply cracked section stiffness modifiers to represent real reinforced concrete behavior. In real RCC structures, members crack under service loads, reducing their stiffness. ETABS linear analysis requires us to simulate this behavior using property modifiers. Beam cracked section modifiers. First, select all beams. Go to Assign Frame Property Modifiers. Apply reduced bending stiffness for beams. Typically, we reduce major bending inertia to around 0.35 of gross inertia. This reflects flexural cracking in beams. Click Apply and OK. Column Cracked Section Modifiers. Now select all columns. Go to Assign Frame Property Modifiers. Columns also experience cracking but usually less than beams. Apply appropriate reduced stiffness values for columns as per recommended practice. Click Apply and OK. Slab Cracked Section Modifiers. Now select all slab elements. Go to Assign Shell Property Modifiers. Reduce slab bending stiffness to simulate cracked slab behavior. Apply appropriate modifiers for slab bending components. Click Apply and OK. Step 8. Define and apply wall loads. Now we will define masonry wall loads. Go to Define Load Patterns and create a new load pattern named Wall. Now calculate wall load using wall thickness, story height, density of masonry, and deduction for beam depth. Convert this into a line load in kN per meter. Select supporting beams and go to Assign Frame Loads Distributed. Apply the calculated wall loads to the respective beams. This step is critical for accurate gravity and seismic mass modeling. Step 9. Apply superimposed dead load and live load on slabs. Now we will apply floor loads on slabs. Select slab elements. Go to Assign Shell Loads Uniform. Apply superimposed dead load, such as flow finish, waterproofing screed, etc. For example, assign 1.2 kN per square meter as superimposed dead load. Now, assign live load based on building usage. For example, residential or office live load such as 3.0 kN per square meter. For terrace slabs, apply terrace live loads separately such as 1.5 kN per square meter. Save the model after assigning slab loads. Step 10. Define wind load as per IS 875 Part 3. Now we will define wind loads. Go to Define Load Patterns. Add wind load patterns. Wind plus X, wind minus X, wind plus Y. Wind Y set load type as wind and select IS 875 Part 3. Define wind parameters, basic wind speed, terrain category, structure class, risk coefficient, topography factor. Define wind direction angles such as 0 degrees, 90 degrees, 180 degrees, 270 degrees. This ensures wind is applied from all critical directions. Step 11. Define mass source for seismic analysis. Now go to Define mass source. Define mass source based on 100% of dead load and a specified percentage of live load as per IS code. This mass source is used for seismic force calculation. Correct mass definition is essential for accurate base shear and modal analysis. Step 12. Define response spectrum functions. Now we will define response spectrum functions. Go to Define Functions Response Spectrum. Select IS 1893 is to 2016 response spectrum function. Define spectrum for X direction, Y direction. This function represents spectral acceleration versus time period. Step 13. Define response spectrum load cases. Now go to Define Load Cases. Add a new load case named RSX. Set load case type as Response Spectrum. Assign response spectrum function in X direction. Similarly, add another load case named RSY for Y direction. Apply appropriate scale factors as required by code and units. Click OK to save load cases. Step 14. Final model analysis. Now save the model. Click on Analyze Run Analysis. ETABS will now analyze the structure with gravity loads, seismic loads, wind loads, cracked section stiffness, diaphragm action, and response spectrum cases. Step 15. Post-analysis checks. After analysis, we will check modal mass participation ratios, base shear values, story drifts, story displacements, and overall structural behavior. If any warnings or errors appear, we will resolve them before proceeding to design. In the next video, we will go deeper into interpreting seismic results, checking drift limits as per code, understanding modal shapes, and starting design verification. Thank you for watching.